So, welcome to the SBGames technical session called Computer Graphics and Virtual Reality. That's the first session about this theme. We have 5 papers in this session. Each presenter has around 7 minutes video, followed by a 3-minute live answer question session. And please write the questions using Hoova and do not wait until the end of the presentation to do it because there is a delay. And so in order to not to waste any time, I have the pleasure to invite the first paper, Procedural Generation of Favela Layouts on Arbitrary Terrains, and it will be presented by Nathan from the University of Santa Maria. So please.
Hello everyone, my name is Nathan Bervel. I'm a student at Universidade Federal de Santa Maria, and I'm here to present the procedural generation of favela layouts on arbitrary terrain. Procedural generation of content is a very important topic. Since nowadays the games have big open worlds, automatic generation of parts of the scenario is needed to reduce the workload and development time. As example of procedural city generation, this Venegas work have very good results for standard cities. But what we focus here are shanty towns, a very peculiar settlement, generally with irregular buildings, that differs from normal cities in various aspects. They can be placed in overly inclined terrain without almost any foundation. Short space to build generates very narrow alleys between the buildings. And upper floors built at different times and with different resources makes them to be very contrasting from each other. And so, our work focuses on the procedural generation of favela layout, road creation, building distribution, and generating simplified 3D structures, since at this point we do not focus on generating detailed models. But what is the use of a favela layout in the game segment? Here is an example. The game Descenders is about downhill bike racing. One of its map is a shanty town that is procedurally generated. As the houses only need to be there as obstacles, they are very simple. And since the player do not interact with the buildings and alleys, the houses do not need to be correctly placed on the ground. Another example is the Microsoft Flight Simulator, which generates a representation of almost the whole world based on satellite images. The city quality seen from the sky is very nice, but up close we can see that the buildings are very bad placed on the terrain. Our work can be represented by this workflow, where as input we have the terrain height map and a polygon representing the border of the favela. As the first step, a road network is generated, followed by the displacement of the terrain around the road. In sequence, the division of the block based on the roads, building distribution inside each block, and the construction of 3D structures. So to generate the roads, since the Brazilian favelas generally start from the mountain foot and expand over to the top, so do our approach, generating a road network from bottom to top and trying to follow a path that facilitates the traffic of people and cars. To calculate the best path, a star algorithm is used, having as cost the difference in terrain elevation. As we generate 2 points where the road should begin and end, the idea is to try different paths between the points to get the one with the best results. As shown for the first road, 2 points are selected on different sides of the border. The path is calculated between them, and then new road branches can be generated from the initial one. The number of roads, minimum road distance, resolution, size, and maximum angle can be influenced by parameters. As for the buildings, blocks are generated adjacent to the roads. Limited at roads corner, each block is a polygon where the buildings will be distributed. As such, the block adjacent to the road are drawn in blue, and inside each one the buildings will be aligned to the nearest road. For the blocks not adjacent to roads, Polygons will be generated to fill the remaining space and set an arbitrary rotation for the buildings. The next will be to distribute the buildings inside each block. We use an irregular quad tree to divide the spacing in individual building lots. Between the houses, there needs to be enough space for people to walk. The houses on block borders are compared to the adjacent blocks in order to check collision. This is a block example, adjacent to a road. Around it, a rectangle will be created, aligned with the road. Inside this rectangle, a quad tree is refined until all nodes can be subdivided without breaking a minimum size parameter. Some of lots are divided in parts if they are much long, to not generate skinny structures. In the next step, nodes almost entirely out of the polygon are ignored. As for the ones inside, are generated the base of the building, limited in a way to let enough space for the alleys. At this point we have the base of the buildings, so next step is to construct a 3D representation of them. As we are not concerned with model details, we use a box for each floor. The generation of the floors is based on a set of parameters with an average and a maximum number of floors. Each one can have a size slightly different from the others. Also, an entrance represented by other model is generated from each building, facing the road or an alley. As a result, we could generate some good-looking favela layouts, similar to the objective image of the Rocinha shown at the beginning of the presentation. Here, some more visual results can be seen: a road, a top-down view, and inside an alley. We did not focus much on the time analysis, since a small change in the parameters can result in very different values, but here we have some tests made in areas of 25, 50 and 100,000 square meters. That shows that the building's time increases fast as the map size increases. In conclusion, we have presented a simple method to generate a favela layout with a nice visual result. Even though the structures generated are boxes, they can be easily replaced for more detailed models. And the use can vary for games, animations, and simulations. For the next step, lots of improvements must be incorporated in this work. Complex house models and materials can be generated procedurally. Different kinds of structures can be made, and buildings with accessible interior can also be studied. City properties such as road imperfections, light poles and electrical wiring, vegetation, and the adaptation of the map to consider forests and rivers will turn the work much more realistic. And also very important, to speed up the process in a way to try to reach real-time execution. That's the work. Thank you everyone for watching.
Thanks, Nathan. Thank you, Nathan, for your presentation. And let's see if you have any question. I cannot see anything in the YouTube section. Also not on Hoover. So let me ask you a question. It's not within the scope of your work, but I cannot resist to ask you if you do you see room to introduce aspects of culture in the simulation. I mean, the culture influencing the modeling and the texture. So sometimes you have a Rocinha, sometimes you have another favela in another country, perhaps.
Yeah, we focus more in the Brazilian favelas. They have some differences than the others. Basically, the idea to start in the foot of a hill and go upwards, making this very vertical kind of settlement, is a characteristic more seen in Brazilian favelas. Other characteristics can also be considered, can also be think to grade the idea, right?
Right, great, thank you. So Yes, the audience thing is a little bit shy, no doubt about that. And well, I have a lot of questions, but you have no time to do that. But I'm curious about the performance. If you have a very dense population and you have a very dense simulation,
Okay,
you have
it's
any comment about that?
is a little bit problematic once the size of the outer borders increase. So the buildings can achieve like 10,000 buildings, 20,000 buildings, and it's almost impossible to simulate it on the computer. But focusing on smaller areas works great in 1-2 seconds.
Great. So thank you, Nathan. So send my regards to Pose. You have a great team there, and I'm a great fan of your work. Okay,
Thank you.
so let's go to the next paper. So the next paper is Go Through, a tool for creating and visualizing impossible 3D worlds using portals. And it will be presented by Luca.
Hello everyone, I'm Luca. I'm a research assistant from Voxer Labs at UFP, and today I'll be presenting the work entitled Go Through, a tool for creating and visualizing impossible 3D worlds using portals. So, first of all, some context on what will be presented to you. Computer games are usually placed in a virtual world. Some of those worlds don't follow the same physical rules as ours, creating a sense of confusion. Games like Portal, Antichamber, and the Stanley Parable have fascinated their players with clever designs. The creation of such spaces is not trivial and involves breaking some rules assumed to be true by most 3D engines. Additionally, portal creation tools are usually not open source and not easily accessible. With this in mind, GoThrough was developed as a tool to aid content creators in the task of creating such scenarios. Now, I'll provide a brief overview of how GoThrough works. GoThrough enables users to create 3D worlds containing portals. A pair of connected portals in GoThrough maps separate points in space. Portals have two main characteristics. One, you must be able to see what's on the other side of a portal when looking through it. And two, objects must be able to travel smoothly through those portals. Our pipeline consists of a few steps performed before any handling takes place, followed by some steps performed for every camera. Travelers are objects enabled to travel through portals. Every traveler that is crossing a portal has to be handled on both sides of it. For this, we use a clone of the traveler's mesh. With this in mind, the first 3 steps are performed to correctly place and configure travelers and their clones. First, travelers crossing portals are detected. Second, they are teleported to the other side of the portal if needed. Last, the clone is placed on the opposite side of the portal, and an alpha clipping shader is assigned to both meshes. Go-through is a textured-based approach. This means portals are meshes textured with the output of a virtual camera. Once the travelers are properly positioned, 3 steps are executed for each camera enabled to render portals. First, an inner-facing mesh is placed behind each portal. This avoids clipping of the portal by the camera. Then, a visibility tree is assembled containing information about which portals are visible. This tree is used to treat recursive cases where portals are seen inside other portals. The tree is then traversed in a depth-first order to render the visible portals. The virtual camera uses an oblique function to align its clipping plane with the destination portal, hiding any objects between them. Finally, portal textures are sampled in screen space when rendering. Some guidelines on the use of portals is also provided. Some problems may arise when using portals. Illumination inconsistencies such as wrong shadows in the surroundings of a portal are a common problem. We provide some guidance on how to design your scenes around these as well as other issues. More details can be found in the paper. We have also made some analysis on the tool's performance. 2 experiments were carried out. The first had 2 portals facing each other, and we increased the maximum recursion depth. This created visibility trees of breadth 1 with increasing depth. The second had a limited recursion depth of 1, but we increased the number of portal pairs. This created a visibility tree of a depth 1 with increasing breadth. Our results show that a greater number of portals tend to be more costly than a deeper recursion level. This occurs because more textures have to be allocated and more texture swaps have to be performed. Once the VRAM is taken up, RAM, which is much slower, is used, making those swaps even more costly. We also performed some experiments on users to evaluate the tool's usability. 12 users were interviewed. The interview consisted of an introduction to the concept of portals and the tool they would be using, a guided experiment where users would reproduce a scene by following a series of steps, a free experimentation where users would try out things they like, and a SEALS questionnaire to evaluate the tool. Our tool obtained an 87.5 SEALS score, which can be classified as excellent or A+. Next, I'll show you some possible use cases of our tool. Those scenarios aim to provide insight on possible mechanics achievable through the use of go-through. First, an impossible geometry example, a square room with 3 corners. Second, a house of mirrors, where 4 self-connected portals are placed on the sides of a rhombus. Third, an infinite corridor, where a pair of connected portals is placed facing each other. And fourth, an unsolvable maze that morphs itself whenever the player moves to another room. In conclusion, in this work we have provided a literature review on the subject going back as far as 30 years, supplemented by a gathering of web resources. This academic and industry knowledge was compiled, adapted to the video game scenario, and carefully explained. A creator-friendly tool was then developed and evaluated, and is freely available to the academic community. We hope this can make portals more accessible to creators. Use case suggestions, detailed performance analysis, and some usage guidelines are also provided. Thanks for watching, everyone.
Thank you, Luca. Very insightful paper because you are bringing interesting questions. It's an old one, including portals in virtual reality, now in games as well. Let me see if you have any question. Yes. I'm very happy. The first question in the Huba. Is go through open source? Is the question.
Yes.
Where can I find it? Is a question by Alison Henrique.
It is on GitHub. I can post the link in the chat.
Great. So do
Okay.
it, please, Luca.
Okay.
Quite happy about that. And any other question? No. So let me ask you something. Depending on the teletransportation you do, sometimes you may lose the sense of presence, the sense of immersion. Have you considered that? I mean, for the future, I mean, because you can use the portals to make a big jump into another environment, and people can feel some.
Okay. If the camera is passing through the portal, the teleportation occurs smoothly, you know? There is no visual gap.
Yes, but you can make a transition, use the same tools to go from one level to another one, like a real portal. I mean, from the fiction, science fiction, and then that time because you are going from one floor to another floor, and so you can use some sort of portal. So that's a suggestion I made to you, because it's an old question with no proper answer yet. and so you have all the tools to make experiments and all that.
Okay.
Well, all right. So no other questions. So thank you, Luca, for
Thank
your
you.
interesting
Bye-bye.
paper. And so let's jump to the next one. So the next one is moving virtual agents forward in space and time. It will be presented by Gabriel from the PUC Rio Grande do Sul. So please.
Hello everyone, my name is Gabriel Fonseca Silva. I'm a master's student at PUC in Brazil, and I'm going to present a work titled Moving Virtual Agents Forward in Space and Time. Since the pioneer work proposed by Thalmann and Moose, many other methods were proposed for crowd simulations, including the exploration of crowd densities, heterogeneous behaviors, and personality traits. Still, few of them tackle the problem of fast-forwarding a simulation while maintaining a coherent path with minimum error. In this work, we propose a model for fast-forwarding virtual agents in crowd simulations. To achieve that, we integrate a position estimation model with a global path planning algorithm. In addition, we included personality traits in agents that affect their behavior during the simulation and the fast-forwarding process. For related work, Peter et al. Presented a method of level simulation based on a camera viewpoint. Osborne and Dixon presented a similar method for grouping agents using a hierarchical level of detail. Guy et al. Proposed a parallel method for local collision avoidance using velocity obstacles. Finally, the model presented by Bianco et al., which our work is based on, estimates future position of agents based on a pedestrian dead reckoning model. The model proposed by Bianco et al. Is comprised by four main steps: the interaction with people factor definition, related to nearby agents; the environment complexity factor, based on the total area of obstacles in the environment; the pedestrian dead reckoning steps, which estimates future positions; and the repositioning of agents in space. Their model uses the crowd simulation method known as biocrowds, and thus we also do. In our model, named fast-forward adaptation, we propose the removal of the environment complexity factor, since it may take into account the area of an obstacle even when not obstructing the path of an agent. Instead, we made two alterations: the inclusion of a navigation method and the position estimation within the defined path. We implemented the A-star global navigation model proposed by Hart et al., which allow agents to circumvent obstacles toward their goals. During the continuous simulation, agents follow their defined path. Once a target frame t is reached, the continuous simulation is paused. The future position of agents at frame t plus delta t are estimated in a straight line using the PDR method as presented by Bianco et al. The total magnitude of the jump is calculated, representing the expected travel distance. Then, we project this magnitude into the global path of the agent, identifying the point with the same travel distance. The agents are then repositioned in space and their path planning is updated. Finally, the continuous simulation resumes from frame t plus delta t onwards. To include personality traits to our agents, we choose the Ocean Psychological Traits model proposed by Goldberg, which stands for openness, conscientiousness, extroversion, agreeableness, and neuroticism. Each agent in the simulation receives a set of ocean values, ranging from 0 to 1. Then, a relationship between ocean traits and behaviors is established based on Ob et al. The following group behaviors were added to agents based on their ocean values. The equations presented are defined in the work of the Rupinar et al. The walking speed behavior defines the desired speed for agents inside their group. When a strong leader is present, other agents follow its behavior, ignoring their features and assuming the features of the leader. Groups with impatient agents have a lower cohesion, tending to spread more from each other. Also, impatient agents aim to reach their goals faster. I will now present the results achieved by a method. For our tests, we performed 5 simulations of each case with varying number of agents, groups, and obstacles. Then, we calculated the mean values of them. Summation errors were computed as defined in the equation below, where CS and FFA represents the position of an agent at a given frame in the simulations without the fast-forward and with our fast-forwarding method. The error is the average Euclidean distance that represents the difference between the continuous simulation and our method in meters. First, we evaluated the FFA method. Agents should be able to jump from its position in time x to a future position in time y in the most accurate way possible. We model an environment of 900 square meters with 4 simulation scenarios presented in the table below. For all simulations, we run the same experiment with and without the FFA method and with and without obstacles. As presented in the tables, the continuous simulation presented a higher simulation time than simulations with the FFA method. It means that, when using the FFA method, simulations were able to finish faster. Also, the average error in positioning of agents is lower than 2 meters for all cases. This demonstrates that our method is capable to reduce simulation time without needing to compensate for big loss in precision. We also evaluate if the fast-forwarding method is being influenced by the personality of agents. All simulations were executed with fast-forwarding using the simulation scenario 3. 4 tests were made with this configuration. The ocean values of all agents in each test are presented in the table below. As presented in this table, simulations with a high leadership value presented a much lower simulation time, due to agents following their leader at a quicker pace. Agents with the impatient trait also aim to reach their goals faster, giving lower priority to group cohesion. Also, simulations 2 and 4 take more than double the number of frames than simulations 1 and 3, due to the lack of a strong leader and inclusion of the patience trait, further increasing the contrast in simulation time. The difference value represents the average distance in future position of agents between the simulations with only the FFA and FFA with ocean. Simulations 2 and 4 present a higher value due to the slower average speed of agents. In simulation 1, agents deviate from their path to follow their leaders, increasing their difference. Finally, in simulation 3, agents focus on their paths, similar to the behavior without personality traits, which is indicated by the lower value. We also performed a comparison with the model proposed by Bianco by reproducing the scenarios presented in the work. The figure presents the average relative error for 5 executions of each scenario. It can be observed that our proposed method achieved a similar error for most scenarios, indicating that the precision of position estimation is maintained with the integration of a global path planning. Finally, as a use case, we integrated our model with a simple fog-of-war system, where a CPU player controls the movement of agents. Once an agent enters the fog-of-war, he is placed in a suspension state. The global path of the agent is used to estimate its position at future frames. If, at a given frame, the agent would be in a revealed area, he is moved from the suspension state. This work presented the FFA model to accurately fast-forward agents in time. Future position of agents are calculated taking into account the original global path, obstacles, and nearby agents. Also, we included personality aspect on agents, which is taken into account when jumping to a future position. These are the references I used in the presentation, and thank you very much.
Thank you, Gabriel. Very interesting paper. A lot of questions, at least I have, but I'm still looking for the audience. Is still very shy, so no question up to the moment. And so, please, Gabriel, tell me, how do you get personality traits? Do you apply a standard method, or how do you do it? And how long does it take to get the right personality trait?
Personality trait. Oh, sorry. The ocean model for personality traits is defined in the work of Goldberg. So it has an extensive background on psychology, and it has been adapted to crowd simulations and virtual agents in a few works as we use as base. The model itself is based on the ocean values that I mentioned, and each value is associated with a lot of behaviors for each agent. So, for example, if an agent have a lot of extraversion value, which is it can be associated with the behavior of desired move speed, so it's a faster agent than the others. So basically, you can have a setup for the agents in your simulation. You can also evaluate different people to estimate their values. You can there are also studies that establish different set of parameters for different cultural backgrounds. So Brazil has a different standard parameters of ocean values from China, from Japan, or from the United States. So there's a lot of studies made based on how to acquire ocean parameters and model them towards behaviors in crowds.
Great, Gabriel. Of course, I think about an application where you have to get the right personal traits of a region or a country or a situation, and then you apply your simulation, and then you have to get real ocean values, and that is quite complicated and controversial.
Also
But
because the values of an the ocean values of a person can vary based on recent experiences, for example. So
yeah. I also very curious about because I think there is plenty of room for many new behaviors you can
yes, of course.
introduce in your. Which one do you think would be more appropriate for future work? I mean, immediately.
We are exploring actually different group behaviors, especially goal seeking, combined with the path planning. So I believe it's one of them. Also, the fast forwarding for basically fast forwarding the group itself, analyzing the all agents inside the group and modifying the estimation, the future position estimation based on the whole group, not individual characteristics. I believe these are the main focuses.
Yeah, I'm a great fan of your team, and Soraya is doing a very good work with all of you. And then I'm so happy there is a question here. So I don't care about the time. There is a question. So Joaquin Net is asking, what is a high leadership for you? So
High leadership, we use the value of 0.9 or higher, which means that it's a person with a higher value of extroversion and a lower value of neuroticism. So in a group where a leader, where there is a strong leader, which means an agent that can guide the other agents of the group without volatile behavior because of the low neuroticism, is identified as a leader. So the groups adopt its features.
thank you, Gabriel. So let's go to the next one. So congratulations. So the next paper is called Towards the Design of Adaptive Virtual Reality Horror Games, a model of players' fears using machine learning and player modeling. It will be presented by Eddie Haley. So please, let's see the video.
Hello everyone, my name is Adriele. I'm a professor at Universidade Europeia, and I'm here presenting the paper Towards the Design of Adaptive Virtual Reality Horror Games, a model of player fears using machine learning and player modeling, which is also co-authored by Bruno Silva and Gabriel Gallo. Almost all horror games are designed to induce fear in players. Fundamental fears, such as the unknown, are inherent to the human being. However, more specific fears, such as darkness and apparitions, are individual and can vary from person to person. When a game aims at intensifying the fear evoked in individual players, having useful information about the fears of the current player is vital to promote more frightening experiences. In this paper, we explore fear modeling and present a new method to identify what players fear in a virtual reality horror game. The proposed method uses machine learning and player modeling to create a model of players' fears, which can be used to adapt in-game horror elements to intensify the fear evoked in players. The game used to test our method is a virtual reality horror game that was developed as part of an undergraduate student project. The game takes place in a mysterious house where the player assumes the role of an investigator that is following some reports of strange events that are occurring there. After arriving at the house, the player finds four unusual plushes that suddenly disappear, leaving behind just a note asking the player to find them. The main gameplay loop involves the player's search for clues to uncover the mysteries that surround the plushes and the house. In terms of horror, the game tries to scare players using traditional horror elements such as darkness, apparitions, unknown sounds, and unknown voices. The proposed fear model is composed of three main components: input, output, and a function. The data used as input to the fear model is composed of a set of statistical features extracted from the gameplay during a time window. These features include percentage of time that the player is standing, walking, colliding, the average walking speed, the average rotation speed, position of the hand controllers on all axes, rotation of the player's head, among other statistical data. In terms of output, the model adopts a set of classes that represent the horror elements that can be predicted by the model and used by the game to cause fear in players. The horror elements were selected based on our research on the main techniques used by horror games to provoke fear in players, of which we selected the ones that were more suitable to the prototype game, which are darkness, apparitions, unknown sounds, and unknown voices. The process of mapping the input data to the output classes is performed by the model's function. In the proposed model, we implement the function using an artificial neural network. Since our method employs a supervised machine learning technique to create the fear model, samples of gameplay sessions need to be captured in order to train the neural network. In order to collect training samples, we invited 18 participants to play our virtual reality horror game for the first time. After playing the game, the participants filled a post-test questionnaire where they rated how much fear they have experienced with each horror element during the game. Each horror element was rated in a 5-point Likert scale, ranging from not scared at all to extremely scared. During the game sessions, the system automatically captured all statistical data used by our model in 6 time windows of different lengths, which is important to identify the time window that provides better results for the classification process. In order to label the samples, we use the player's answers to the post-test questionnaire, where they rated the horror elements that caused more fear during the game. A total of 6 datasets were created, one for each time window. To evaluate the proposed fear model, we performed 2 tests: a precision test to evaluate the accuracy of the model, and a performance test to evaluate the real-time performance of the neural network when predicting what new players fear. For the precision test, we performed 2 experiments. The first experiment is the general accuracy test, where we use the 6 datasets of different time windows to train and test our neural network following a tenfold cross-validation strategy. Although the cross-validation strategy is usually enough to guarantee the generality of the model, it does not ensure that the model has learned what is intended to. Since our model used multiple samples of the same player as input, the model could be learning how to identify specific players instead of recognizing what they fear. Therefore, to ensure the generality of the proposed model, we performed a second experiment to test the accuracy of the model for new players. In this new experiment, we removed all samples of one player from the trained dataset and used them to create testing datasets. This process was repeated for all combinations of players in training and testing datasets. The results of the precision test indicate that the best length of time window is 10 seconds, where the general accuracy obtained for the cross-validation test is 81%, and the average accuracy when classifying new players is 79%. Given the similar accuracies obtained in both tests, we can conclude that the model has learned what was intended to and is capable of recognizing players' fears. For the performance evaluation, we tested the prediction of the horror elements during a normal gameplay session, wherein a total of 62 predictions were performed. For each prediction, we computed the time necessary to calculate the input features and predict what the player fears using the neural network. As a result, we got an average time of 3.1 milliseconds, which indicates the applicability of the proposed method in highly interactive virtual reality horror games without noticeable delays. The main contribution of this work is the new method to identify what individual players fear in a virtual reality horror game, which combines machine learning and player modeling techniques to create a model of players' fears. We have many future works planned, including the validation of our method with a larger dataset, the conduction of user studies to evaluate our method from the player's perspective, and also the possible use of sensors to collect biometric data during the data collection process. That's all. Thank you for your attention.
Thank you, Erdirley. Very, very interesting paper. So let's see if you have any question. No, the Odyssey is a little bit shy, as
They
the
are very
usual.
shy.
Yeah, but of course, look, Delay, you are brave. You have no fear because you are working with a quite complex emotion.
Yeah.
And
Now it's time to understand what players fear in a game.
Exactly. I wonder if in future we can collaborate in order to investigate some semantics behind that. I mean, in the sense that you should look for some interpretation of what the machine learning is doing, because fear is quite complex. You don't know if it's a surprise situation, and also fear depends on a lot of things. So I think you are opening a new line of research. So there is a question. There is a question. Yes, yes, yes. So our dear Soraya, she's asking you, have you think about extract emotions using facial emotion recognition?
Yes, actually, we have another work about trying to do that exactly. So yeah, we are trying to combine now more information, not only gameplay statistics, but also external data, like images from the camera. So we can put a camera in front of the player while the player is playing the game and try to extract data from the image. But for virtual reality, actually, that's not very easy because players are using the headset. So recognizing emotions in virtual reality is a bit more complex because we cannot see the entire face of players. So it kind of gets a bit more complex in order to get the image. But actually, related to that, we are also trying to use the sensors because fear is something that you can recognize by like the beat, the heart rate, or other biological data that we can read with sensors. So we are trying to get more information. The more information we can get from players, more precise the machine learning algorithms can predict exactly the fear. But that also involves psychology, because since you were saying about trying to understand what the machine learning, what the neural network is really extracting from there, it's also important to analyze that from the psychology perspective, because that's a completely different area. So I think it's a very interesting topic of research that we can go and develop many works here, certainly.
Well, great. I think we can stay here talking. Very excited subject. Sora is also saying that people can hide their feelings, real feelings, and so on. But you have to move to the next question. So let's go to the next paper. Thank you very much, Adele. And so the next paper is evaluation of graphical user interface guidelines for virtual reality games. It will be presented by Pauline from the Federal University of Ceará. So please, let's.
Hi, my name is Pauline Jucá, and this is evaluation of graphical user interface guidelines for virtual reality games. The motivation of this work is that many of the traditional practice in design and development of graphical user interface do not fit to the context of virtual reality games, requiring adaptations or the creation of new solutions. The main goal of this work is to analyze some of the graphical user interface guidelines for VR, and from this, investigate the perception of the players about the UI guidelines for virtual reality games that use HMD display controlled by the head orientation. The methodology of this work contains 4 steps. The first one is to analyze the guidelines for user interaction with VR applications available in the literature. Evaluate 5 games that were positively ranked in the Steam platform to understand if these games apply the guidelines found. Identify visual elements that were recurrent during the evaluation of the popular games. Evaluate user perception about these common elements and their suggestions. During the identification of existing guidelines, we have found many studies that identify or suggest guidelines for VR application. The focus of this work is to analyze manufacturers' manuals as Oculus Rift and Lift Motion, and game engine guidelines as Unity 3D. We couldn't find a guideline set for Unreal game engine, so the Unreal was not evaluated. This table presents from each set of guidelines, each guidelines came from. After selecting the guidelines, we had to select the games that we would evaluate. And these were the 5 games selected. It is worth mentioning that the search was carried out during July in 2018, and these values are not the same today. After selecting the games, each game was analyzed through videos, seeking to find conformity with the guidelines already defined. The choice to evaluate the games through video was due to the unavailability of VR equipment. This is one limitation of this work. Videos of other players playing the games were used. These videos were visualized using a generic VR device as a cardboard to allow the immersive sensation of the VR interface. This table presents the results. It is possible to notice that all games evaluated meet the criteria of providing depth tips using a comfortable distance for presenting content and presenting text that can be read and avoid scaling and spacing problem interactive elements in the UI. Most games follow the guidelines identified by the manufacturers, and main unattended guideline was about wearable menus, which most games do not use. The next phase was to evaluate the guidelines with final users. Most of the interviewees were players, but some of the interviewees were also game developers in VR reality. The set of the VR devices used by these interviewees is presented on this list. The users were asked to identify the importance for them of each guidelines. When analyzing the responses, readability was identified as one of the biggest issues of user interface for VR. The interviewees pointed out that the texts are often blurred, pixelized, very small, or are arranged in the peripheral areas of the vision, which makes their visualization difficult. Another major problem pointed out by the interview is related to the breaking of the immersion caused by user interface. It was pointed out that graphical interfaces such as text panels and floating menus are one of the causes for the immersion break. In addition to that many times interfaces are confusing to access and control. The challenging enriches the menus are another point identified by the interviews. According to them, interfaces are often arranged over relatively long distance, make interaction difficult or impossible. Another difficulty presented by the interview is related to the fixed elements in the user's view. The interviews pointed out that interfaces are in the middle of the character path, that they move along with the head, making it difficult to see anything that is behind the interface. Respondents also had difficulty related to orientation when interacting with menus and objects. Some point out that in some cases it is not clear where the controller is pointing because there is no indication. As conclusion, this work aimed to analyze some of the UI guidelines for VR games. From this, investigate the perception of the users about these UI guidelines, as well as investigate whether some VR games are following the guidelines recommendation. This work also recommends some common guidelines, providing depth tips, using in a comfortable distance for presenting content, presenting text that can be easily read, and avoiding scale and spacing problem in interactive elements in the VR UI. Thank you. Hi.
Hi, thank you, Pauline. Very interesting, very insightful, and also necessary work in the industry. So let's see if you have some questions. No, people still shy or going away for some reason. I don't know. All right, so let me ask you, because I'm quite interested in the work, because graphical user interface guidelines for VR games are of utmost importance for software engineers working in the game industry, and the area of interface, human computer interface or interaction is more adequate. Is not giving us the practical answer for the questions, and so you are opening a new area as well, I think, because people are not looking for the software engineer. Need some, they need guidelines, and so I'm quite interested to know if you had to choose just one result from your investigation, which one do you think is most impressive? I mean, that causes you a surprise, or you see, oh, that's something people are not looking at. Yeah.
It is a really nice question. Thank you for this. And I think one of the most impressive things that we found out that some users have the same perspective that we had when we first started this investigation. We think that there are really a lot of guidelines, but they seem to be not so easy to implement. They are more generic guidelines, and they are difficult to put in practice. And we think that the user perception about this is really important. So when we ask the users, they say the same thing, that sometimes the text is difficult to read because they are far from the camera, and sometimes the pointer that we use a lot, it's not easy to use because it's difficult to point something and click, and the metaphor that we import from computers, like pointing and clicking, it's not working to VR. And I think this is the most important thing that we found out. It's
Right.
difficult to put text, and it's difficult to import or use the same types of interface.
Great. Look, I'm so happy now because there are a lot of questions now. And so one is from Joaquim Neto, is how did you choose the guidelines?
We chose the guidelines based on the commercial version of guidelines because we one of our hypotheses is that there are a lot of guidelines, many of them previous to commercial device. And we think that the commercial device made some changes in the perspective of the users or of the players. When the players has access to VR device, they adapt to it, and things that were difficult before because of the cables and the device that was too big and the screen that was not it has not a good resolution, and with the commercial device, the users adapted to it, and they need things that were different. So we tried to find guidelines that were from the industry, that from manufacturers and game engines.
Thank you, Pauline. There is another question, but I will ask you to answer him. It's a question by Luis Fernando Bicalho. And so if you can answer him, so go to the Hoover and answer him, please.
Okay.
Asking why bad VR game is not on the radar. I mean, you to choose it. But answer him that there because you are late. So thank you very much, Pauline.
Thank you.
And thank you for the entire audience. And so this is the end of this session, computer graphics and virtual reality. So enjoy the rest of the sessions. So